Here we have a few examples of differentiation involving logarithms, and these are from our worksheet that we did in class the other day, numbers 30, 31, and 38. Now 30 and 31 are actually, compositions of functions that just happen to involve logs, and they're actually very similar, right? If you look at the two problems, 30 and 31, they look very similar. .30 is the natural log of 5x squared plus 9, the whole thing raised to the third power, whereas 31 is the natural log of 5x squared plus 9 to the third power, right? So only the 5x squared plus 9 is raised to the third power, and then you're taking the natural log of that in 31. So they're different problems. So what you should really do is you should kind of analyze this first. So like 30 is really this whole thing raised to the third. So what I can do is I can call this u. So I can really think of this as u to the third. So if it's u to the third, what would my derivative be? My derivative using the chain rule would just be 3u squared times u prime, right? Or du dx, whatever you want to call it. So that's basically really it. I mean, that's my answer, except I have it in terms of u, and I really need it in terms of x, obviously, right? So now I just go back and I plug in, I replace u with the ln of 5x squared plus 9. So this is really going to be 3 times the ln of 5x squared plus 9. That whole thing raised to the second. So that's 3u squared, right? And then I've got to multiply by u prime, right? But now the problem is u is itself another composition, right? It's really the ln of v, let's say. So I can think of u as being equal to the ln of v, where v is going to equal 5x squared plus 9. So what would u prime end up being? It would really be v prime over v. But again, v is going to be equal to 5x squared plus 9, right? So now all I'm going to do here is replace, I don't want to show that. All I'm going to do is replace v with 5x squared plus 9 and v prime with 10x. Right? So this was kind of like a chain rule inside a chain rule, because it was really the composition of three functions. So what do I end up with here? I end up with f prime of x equals 3 times the ln of 5x squared plus 9, that whole natural log squared, and then I'm going to multiply that by v prime, which was 10x, over v, which is 5x squared plus 9. Can I clean this up a little bit? Yes, I can, because I can actually take the 10x multiplied by 3, and that becomes 30x over 5x squared plus 9, and then I'm multiplying this by this natural log of 5x squared plus 9, the whole thing squared. So that's what I would want as my derivative, right? So what it really came down to is it was a chain rule inside a chain rule, right? I had u to the third, took the derivative of that, but then u itself was actually another composition. U was actually the ln of v, so then I had to take the derivative of v, right, which was 10x. So chain rule inside a chain rule for that one. And now it looks like 31 is probably going to be similar The difference is, this is actually, in 30, u was that whole natural log of 5x squared plus 9. In 31, I can look at u as if it's 5x squared plus 9 to the third power. So I can really look at f of x as being the ln of u, right? So that means that f prime of x is going to be u prime over u. Okay, so it's going to be u prime, and we'll get to u prime in a second, over u, which I just said was 5x squared plus 9 raised to the third power. Right? But now here's the problem. U itself is really 5x squared plus 9, which I'll call v, to the third. So u prime is actually going to be 3v squared. But of course, v is 5x squared plus 9. And we also need v prime, which is going to be 10x, right? Because u prime is actually going to be 3v squared times v prime. So what do I have now? I can now write this all in terms of x, because I can replace u prime with 3 times 5x squared plus 9 squared times 10x, right? That's my u prime, over 5x squared plus 9 to the third. And of course, the nice thing here is that this will actually simplify, because this will cancel out with 2 of those, and I'll end up with just 30x over 5x squared plus 9. So now when I see this actually in this simplified form, it kind of makes me think, hey, I might have been able to do this a different way from the beginning. And in fact, you actually could have, if you had just initially realized, hey, this is really the natural log of an expression to a power of u to the third, right? So I can actually use my power property of logs and take that power out front. So I could have initially written f of x as 3 ln of 5x squared plus 9. And now it's much simpler, because now it's just the ln of u, and the derivative of the ln of u is just u prime over u. And if I have a constant times a function, the derivative is just the constant times the derivative of the function. So in this case, it's 3 times u prime, which is 10x, over u, which is 5x squared plus 9. So then this just becomes 30x over 5x squared plus 9. And that's why it's useful to know these properties well. Now we also have one final problem that involves logarithms. And you might look at this and you say, Lopez, that doesn't involve logarithms, it's just a rational function. True, it's a rational function, but it's actually a product and quotient of just expressions to powers. So when we have this, I mean, could we use a quotient rule inside of which would be a power rule? Yeah, we could, but I think it's probably going to be easier for this one especially to do this by logarithmic differentiation, which means, if you recall, what we will do is we will just take the natural log of both sides right? And then use our properties of logs to rewrite the right side as a sum and difference of logs, right? So when I would first intro the log properties in pre-calculus, I would pretty much give you a general rule that would say any factor that's in a numerator is going to be positive, any factor that's in a denominator is going to be negative. So what's going to happen here is the x minus 1 to the third is going to be positive, and then both the x and the x plus 3 to the fourth are going to be negative logs, right? And I just also use the power property to take the exponents out front. So I'm going to end up with 3 ln of x minus 1, that's the positive one, minus the ln of x, because that's the first one in the denominator, and then minus 4, take the power out front, ln of x plus 3. Okay? And now I will take the derivative of both sides of this equation, right? The derivative with respect to x. So remember, what happens is on the left side I'm going to have to use implicit differentiation. So the derivative with respect to x of the ln of y was y prime over y, if you recall, because it's, the derivative of the ln of u is u prime over u, but here u equals y. So it becomes y prime over y. And now I take the derivative of each individual term here. The derivative of 3 ln of x minus 1 is just going to be 3 times 1 over x minus 1. The derivative of the ln of x is just 1 over x. And the derivative of ln of x plus 3 is just 1 over x plus 3. So what we have here, if I just want to simplify this, is 3 over x minus 1 minus 1 over x minus 4 over x plus 3. And then if you remember how to do this, all we do now, this is y prime over y, and y prime is what we're trying to solve for. So we just multiply by y on each side. And we're essentially finished. It's y prime equals this whole expression, which is 3 over x minus 1 minus 1 over x minus 4 over x plus 3. And I'm multiplying this by y, which I have an initial expression for, right? It was actually x minus 1 to the third over x times x plus 3 to the fourth. And now everything is just in terms of x, so I'm good. Right? Now, is that the prettiest derivative in the world? No. Now, could you do a little something to it by distributing? Yeah, you could, but at this point I would just leave it in this form.